Okay, we're going to continue lecture 3. Now, we're going to start with something that we mentioned earlier. Earth, gravitational field, our building, and the usual assumption that we have this homogeneous, this uniform field where we can describe it as an acceleration of 9.8 meters per second squared throughout this building on this floor, at different wings of the floor, up at the top, down in the basement. So everywhere we have basically this uniform field, it's all gravitational acceleration of 9.8 meters per second squared down, right? So we're now going to look at a particle. I let go something over here, it falls down to the ground. I'm going to describe it as accelerating, and if there's an x-coordinate attached to this particle, on the frame of the particle, then we're going to relate to each other's measurements according to this. X prime is equal to, let's say, the x of the falling frame, plus or minus, depends on how you define g, times t squared, right? This is simply the acceleration formula. So if one says that it's standing still, and the other one says it's accelerating, the relationship between the two, obviously, is given by one of the other's x, plus or minus, whatever, half gt squared. Now, when I'm standing here, when you're standing or sitting and watching this, what are you actually feeling? We discussed this. You're feeling the normal force on you coming from the non-gravitational forces, the electromagnetic and basically, at the end, quantum mechanical, etc. forces in all the materials, and that's pushing up on you, and that's what you feel. And if you take everybody and all the pieces of furniture, and they have different masses, some of them have a large mass, some a small mass, and whether they're sitting or standing, they're going to be feeling different normal forces. The one with the large mass is going to feel a weight that is determined by its mass, and this one is going to feel a weight determined by its mass. And it's going to feel this normal force due to its weight. Now, if you divide by the mass, of course, you end up with g. So there is an equivalent accelerative push up that's exactly equal for all of them. It doesn't matter what piece of furniture or what person or what mass or what density or what size, there's an accelerated push upwards. And as we mentioned, that is completely indistinguishable from some kind of a interplanetary building, rocket, which is all the way maybe in intergalactic space, totally empty of matter. There's no gravitational field that's measurable, and there's nothing even visible, maybe no galaxies visible anywhere nearby. And everybody in that building is feeling that acceleration. And since it's just an acceleration, then obviously it doesn't matter if you're on the third story or the second story, the first story, or what side of the building you're on, you're all feeling, you all have exactly the same acceleration, and therefore you're going to feel exactly the same accelerative push, so to speak, on your feet, irrespective of your mass. Obviously it doesn't depend on your mass, it depends on the acceleration that this rocket ship building has. So there it's no surprise. What's surprising is that in gravity it happens that way, that everybody here feels the same accelerative push. And that's why we can model what's happening here in this building on the planet Earth with an intergalactic traveling spaceship building. And any measurement that we make will be the same in both. They're indistinguishable. Now, the strong equivalence principle claims that any physics experiment that one would make in empty intergalactic space in this interplanetary rocket building would give exactly the identical results. An electromagnetism experiment, light experiment, anything will give exactly the same results as here on planet Earth. In other words, if you want to know how does gravity interact with some other force phenomenon, and you wanted to do an experiment here in the lab, and you were wondering how to do the equations, you could, if you want, just go into intergalactic space and do the experiment there in a rocket. Now, of course, you say, well, it's kind of difficult, I don't have the budget for that. So what do? So we can do just ignore gravity, pretend there's no gravity, and just write the equations for an accelerated platform or rocket or building, whatever it is, and put in your phenomenon there and just see how it would work in an accelerated frame. Okay, so equation-wise, what's the transformation? We have one sees the other according to this. All right? So now, in a real gravitational field, of course, like in the Earth, where you have different strengths depending on the height, so the top floor of the building obviously has slightly less gravitational acceleration than the bottom floor, and different wings of the building have a slightly different direction towards the center of the Earth. So you're going to have regions. This is our building over here. This is a building in some other country on the planet. This is a building on the other side of the planet. Everywhere, there's going to be some region where, in that region, it's going to be a uniform gravitational field, just that it'll be pointing in a different direction than our uniform gravitational field. And if you have a really tall building, then maybe we'll have to divide it into 2 or 3 different uniform regions. And in an arbitrary gravitational field, where you can have all kinds of different field directions and strengths, you can always find some small region, and if it's a very strong field, you might have to find a very strong region in some planet that's very, very dense. Maybe every floor has to have its own little g. One will be 12.6, and upstairs it'll be 10.4, and in the basement it'll be 15 point something, right? But you can always find some small region where, to the extent that you're able to measure, you have pretty much a uniform field. And so we'll model any gravitational field by a collection, a very large collection, maybe even an infinite collection of tiny or infinitesimal regions in each of which we can consider the field to be uniform. Now, again, remember, that's any gravitational field, all right? It's this collection of uniform fields. So, since we can model any one building with a rocket, we can model this collection with a collection of rockets. So, this is a gravitational field, arbitrary. Each building, so to speak, each region has its own uniform field. In each region, we can model it by an acceleration. We'll produce an acceleration in this region would produce exactly the same phenomena as would be measured in this building, right? If this is a building in a gravitational field. And so we can then model all of these buildings, so to speak. Of course, they're not building the regions of space. We can model each of those with an acceleration. So whatever would happen in this gravitational field will happen in intergalactic empty space, where we create a region far from any gravity. This is gravity. We take a region far from any gravity, far from this field, and we simulate it. We model it by putting in these plates or buildings, accelerated rockets. And in each region where there's a rocket, there'll be 2 phenomena. Any inertial particle that you let go from outside will seem accelerated by those in the plate, which models exactly what happens if you're standing in the building and you let something go. It looks to you as accelerated. And in the same way that here, those who consider it accelerated will feel this accelerated push on themselves that we call the normal force to our weight, will also feel an accelerated push on their feet over here that obviously to them will be due to the acceleration. But this situation of this collection of rocket plates is completely physically indistinguishable from the situation of gravity, let's say, of the planet Earth, all these buildings, and the free fall particles, and so on. So we have this very interesting idea that we could model an arbitrary gravitational field by a collection of regions, each of which has a uniform acceleration. Now, what is a uniform acceleration? We know mathematically it'll give us this, but let's look at it, since we know that we're talking about spacetime, let's look at it in a little bit of a more sophisticated way. So, a straight line in space, y is equal to mx plus b, the xy axis. A straight line in spacetime, as we spoke about, our inertial particle world lines have straight lines. X is equal to vt, v would be the speed, or the inverse of the speed, and it's the slope of the line in the tx. All right, so this slope over here is the inverse of the speed. And so vt, the speed times t plus b, that's a linear relationship between the two. All right, so this is the equation of straight line. And you can do a coordinate transformation in a regular xy plane. Let's say something like this. You can do a coordinate transformation also in xt. If you have an xt, right here we're only considering 2 dimensions just for simplicity. So we have these 2 dimensions, time and 1 dimension of space, but we're talking about linear motion being accelerated, let's say, straight down. And the relationship between the two can be something like this. In the same way that we have a coordinate transformation in this plane of space, we can have a coordinate transformation in this plane, so to speak, of space-time. And so we see this equation as a coordinate transformation. So in other words, going from the viewpoint of the planetary surface to the viewpoint of the free-fall particle. The free-fall particle claims it's inertial and we say it's accelerated. We see it as a coordinate transformation in space-time. It's a space-time coordinate transformation. Okay. Now, a coordinate transformation can't ever change physics. Coordinate transformation is just a different perspective. Like here we have a particle falling, we have ourselves, we describe it one way, the particle described, the frame of the particle describes itself in a different way. The description is not going to change the actuality of what's happening. It's a perspective. And one should always be able to change from one perspective to the other if one understands the physics. So in a uniform field, in a uniform gravitational field like in this room, at least according to the usual approximation, we can model what's happening with a coordinate transformation in space-time. And we know that if we use these kind of coordinates, we're going to see the inertial particles as accelerated. If we use the free fall particles coordinates, then it won't be accelerated. It'll see us as accelerated, which is fine because we feel these accelerated forces. So we're not inertial. We're not surprised to find that this inertial particle considers us to be accelerated. But basically, in the same way that we were able to see an arbitrary gravitational field as a collection of accelerated plates or buildings, we can now see each of those accelerated plates or buildings as a coordinate transformation in space-time. A type of coordinate transformation which, of course, does not change any of the physics. It's just changing the description. But we have a multiplicity, many, maybe an infinite many, regions in each of which there is some coordinate transformation. This one will have some x prime 1 is equal to x plus 8 t squared, and this one has a different coordinate x prime 2, which is x plus b t squared, and so on. You'll have a whole bunch of different regions. Each one has its own acceleration, and therefore each one has its own space-time coordinate transformation. Now we have a very interesting challenge. How do we find a mathematical model of this? We have the mathematical model which tells us we can model any arbitrary gravitational field by a collection of regions in each of which there is a coordinate transformation in spacetime. And we know that in each of those regions the coordinate transformation just changes the description, it doesn't change nature. So we want to find some situation and its corresponding mathematics which has exactly this property, but we have to invent it. And it turns out curvature is the answer. What kind of curvature? Well, if you take let's say we had this tx or xy, right? And you have a description that uses curvilinear coordinate axes instead of, let's say, these rectilinear and perpendicular coordinate axes. We're going to use some kind of curved lines as our coordinate axis. And you do transformation from one description to the other. Then obviously you get a coordinate transformation and you're going to get all kinds of different terms arising. What seems like a straight line in one coordinate system, like this, if you start using some kind of weird transformations, you're going to get all kinds of stuff over here that's not going to be immediately recognizable as a straight line. But by doing a coordinate transformation, you can't turn a straight line into a non-straight line, or vice versa. What you can do is take a straight line equation that's immediately obvious as a straight line equation and turn it into something that's still describing a straight line, but in a very non-obvious way. Okay, you can change the description, not the actuality. So we can see that we have here a collection of regions, in each region of which what we're doing is equivalent to using curvilinear coordinates. Curvilinear coordinates simply means if you're going to change something like this, obviously this new x prime is not a straight line as the xy are, right? It's going to be something like a y squared, okay? So here what we're doing also is kind of using curvilinear spacetime coordinates, and that's the transformation that we're doing. So what we have is the sense that an arbitrary gravitational field can be modeled by a collection, finite, infinite, whatever, of finitely sized or infinitesimally sized regions, in each of which there is a space-time coordinate transformation. So we're getting more and more sophisticated. So now, what does that give us? What is a collection of regions in each of which there is a curvilinear coordinate transformation, or equivalent to that? And the answer turns out to be, maybe not surprising at this point, curvature. Curvature of the surface. The curved surface can be approximated as a collection of individual flat regions. Each region, just like the surface of the Earth, we consider flat. Our building that we took over here had a flat floor, right? We assume that a curved surface, just like a curved line, if you look closely enough, you're going to find that you can approximate it as a straight line if it's small enough. The same thing, any kind of curved surface, if you look closely enough, you're going to find a region where you can consider it flat to the extent that you're able to measure. Now, that might be smaller and smaller and smaller depending on the quality of your measurement and depending on how curved this surface is. But there will be some region, even if it has to be infinitesimal. So you can approximate a curved surface, or describe it as a collection, maybe an infinite collection, of these regions in each of which there is flatness. And that's called local flatness. You have local patches which are flat, but the totality is curved. Now, obviously, if you have a local patch that's flat and another local patch that's flat and another local patch that's flat, there has to be something that tells you how you go from one flat thing like this to another flat thing like that. They can't overlap. You can't extend any one region out far. Once you start extending it out a little bit too far, it's just not describing the surface anymore. You've gone off the surface. So the mathematics of curved surfaces describes exactly this. You have curvature, and it's real curvature, and it can be intrinsically determined the way that we described before from within the surface, even if it was just a two-dimensional space, not the two-dimensional surface of a three-dimensional object, but it was just a two-dimensional space. You could define the curvature, as we mentioned. And locally, small enough regions will give you everything that you require of something that you consider to be flat. You have local flatness. And that's exactly a model of gravity. So we had previously a model of gravity where there was an existence, we needed a space in which geodesics exist, and despite the individual existence of a geodesic and the fact that an individual geodesic could never know that it was in a curved space, there's no distinguishing between the geodesic of a curved space and a non-curved space, right, or a warped space and non-warped space, and nevertheless, neighboring geodesics would deviate. And now we found that curvature did exactly that. Now we find another property of curvature very much related, which models exactly what we need in gravity. That you have on a curved surface locally flat patches that together the totality exactly models the entirety, where the trick is knowing how to take all these individually flat pieces, because the individually flat pieces don't contain any information about other pieces or how to go and create the entirety, just like the individual geodesics don't. But when you put a few together in the right way, then you get the curved surface. And that which describes this curvature is a tensor. Now, at this point, you're not surprised. And it's the Riemann curvature tensor. So the Riemann curvature tensor, which existed for curved surfaces, is exactly the mathematical tool that we need to describe an arbitrary gravitational field. And what will it describe? It describes exactly this property of, on the one hand, individually flat. On the other hand, two individual flat regions don't exactly mesh, and there's a difference between the two due to the curvature, and that's exactly what the curvature measures, which is exactly analogous, similar, and related to two individual geodesics, each of which is exactly the same as if it would be a geodesic of this flat surface. But when you look at the relative behavior of these two geodesics, you
find that there is deviation, relative acceleration of the separation vector. And that's exactly what the curvature is. So you won't be surprised to find that the Riemann tensor, which describes mathematically precisely the curvature as it relates to these locally flat patches, is exactly what relates the individual geodesic's deviation. The geodesic deviation is measured by the Riemann curvature tensor. That's it.